So hello everyone. Today we'll see the Euler form of a complex number. We already done different forms of the complex number, out of which the Euler form is very powerful form of the complex number. So today we'll see in detail about the Euler form of the complex number. How do we get that form? The proof of getting the Euler form and some of the applications of the Euler form. So z is equal to, let's say, r e to the power I theta. This is the Euler form of the complex number. Here r is the modulus of the complex number and theta is the argument of the complex number. Okay, here the e is called the Euler number, having approximate value is 2.71, just like the pi has approximate value 3.14. so same way e has a Euler number has approximate value 2.71. This is the kind of irrational number. Just like the pi is irrational number, same way this is also a irrational number. Okay, let's take one basic example. Let's say a very basic question. If I ask you whether I to the power I is pure real number or pure imaginary number. Okay, to find whether any number is pure real or pure imaginary, we will try to write in the terms of standard form a plus ib. If we get b0, then it's a pure real number. If we get a0, then it's a pure imaginary number. Okay, so we start with the I, writing the polar form of I. So I is r e to the power I theta, where r is the modulus of I, that is 1, and theta is the argument of I. And if we plot on the Argand plan, I somewhere lie on this vertical axis. So that's why this argument is pi by 2. So this is pi by 2. So I to the power I has a e to the power I pi by 2. The base I is written as e to the power I pi by 2, and the number and the power is I. So it is e to the power I square pi by 2. That is nothing but e to the power minus pi by 2. So essentially I to the power I is a pure real number. Okay, see, this is pure real number, whereas this is imaginary to the power imaginary. So imaginary to the power imaginary may not be a real number, may not be a pure imaginary number. It may be a real number also. So we can clearly see. Okay, so we have done the different forms of the complex number. So will not go in detail, we already done in the previous class. So z written as a plus ib, the conventional form. Then this is also written as r cos theta plus I sin theta. R is nothing but the modulus of z. Okay, how come we get this point? So we can I can show that that any complex number z is equal to a plus ib. This is written as, this is the value is b and this is a. The argument is theta and the modulus z or r is the distance of the complex number p from the origin. So clearly what is b here? B here is mod z or r sin theta, and a is mod z or r cos theta. Now we can say z is equal to a plus ib is nothing but mod z cos theta plus I sin theta. Okay, mod z plus I sin theta. Okay, we also in the beginning of this lecture we told that this is r, or by the way, mod z is r also. So r cos theta plus I sin theta. This is r e to the power I theta. The Euler form in the beginning of this lecture we told that this is r e to the power I theta, whereas we have just converted that the standard form a plus ib can be written as r cos theta plus I sin theta. So what it means? It means that the e to the power I theta is cos theta plus I sin theta. This is a very, very important conversion between trigonometric and the Euler form. Okay, so we'll prove this part. So we'll prove how come the e to the power I theta is cos theta plus I sin theta. We'll prove this thing. Okay, and before proving we have some prerequisite is there. So we'll see some prerequisite things are there. What is prerequisite? First of all, let's say any polynomial is written like this: a0 plus a1x plus a2x square plus a3x cube plus a4 x to the power 4 and so on. Means let's say n degree polynomial, so we have a n x to the power n. And if you want to find the coefficient a naught, so our aim is to find the coefficient of polynomial. Coefficient of polynomial. So we can, if substitute x is equal to 0, I will get f0 is equal to a naught. So the coefficient a naught is nothing but f0. Again, if you have to find the a1, I will have to differentiate this. F dash x is a1 plus a2 2x plus a3 3x square plus a4 4x cube and so on. Okay, let's say n x to the power n minus 1. Here again, if I substitute x is equal to 0, I will get f dash 0 is equal to a1. So the coefficient a1 is nothing but f dash 0. Now if we want to find the a2, so again we'll differentiate this. F double dash x will be a2 2 plus a3 3 into 2 x plus a4 4 into 3x square n into n minus 1 a n x to the power n minus 2. Again here if I substitute x is equal to 0, I will get f double dash 0 is 2a2 or a2 is f double dash 0 upon 2. This is the coefficient a2. Similarly, we can find the a3 is f triple dash 0 upon 3 factorial, and the nth coefficient will be f differentiate n times substitute 0 upon n factorial, or in general any coefficient r term will be f differentiate r times substitute 0 r factorial. This is how we find the coefficient of any polynomial. Okay. Now next we'll talk about the power series. What is the power series? What is the power series? So power series is nothing but the extension or the infinite term of the polynomial polynomial series. Okay, so power series is nothing but the infinite series. Infinite series, since it is an extension of the infinite term of the polynomial series, so they should fulfill the condition for the polynomial. What is the condition for polynomial? Is the power of x should be a whole number. Okay, so it is an infinite series with power of x or the index of x is whole number. Okay, then they are called infinite series. So infinite series means infinite series, that is we have a naught plus a1x plus a2x square plus a3x cube. It goes up to infinite. Okay, and one interesting thing is that any polynomial, and so any function can be written in terms of the power series. Okay, in power series, and this is valid. When is this valid? So this is not that all the function can be written in terms of power series. There is some condition involved. Okay, so by the way, we already done that. If you want to write in terms of the polynomials, in terms of the coefficient, so this is same as I can say a naught means f0, a1 means f dash 0 x plus a2 means f double dash 0 upon 2 factorial x square plus a3 means f triple dash 0 x cube upon 3 factorial plus f fourth differentiation 0 x to the power upon 4 factorial up to infinite. This is how we can write a polynomial, we can write any function in terms of the power series. But it's not necessary that all the function can be written in terms of power series. There is some condition. What is the condition? So that is important. So any function can be written in power series if the following conditions. What are two conditions? If function is differentiable. If function is differentiable infinite times. Why we need infinite time differentiation? Because to find the coefficient of the last term, we have to differentiate infinite times. for first term is constant, second term we have differentiate first times, for getting the coefficient of the third term we have differentiate two times. So it means that to get the coefficient of the infinite term we have to differentiate infinite times. Then only we can write the function into the power series. So that's the first condition, is the function should be differentiable infinite time. Then only we can write in terms of power series, because to get the coefficient of the power series we have to differentiate infinite times. And the second thing is the function is convergent. That is a very important. Function is convergent. Okay. See, there are multiple methods to check whether the function is convergent. So we can develop in future some of at least one chapter of series. So in chapter of series we can see the different methods to show whether, to find whether the function is or any series is convergent or not. Okay, but with a very basic test we use in case of convergent is the ratio test. Okay, ratio test. What is ratio test? So limit n tends to infinity, tn plus 1 upon tn, this is n plus 1th term, that is less than 1. Then we say it's a convergent. Okay. So this is the two things we are required. For example, we can have let's say 1 upon 1 minus x. 1 upon 1 minus x is a well known geometric series. We know it can be written as 1 plus x square plus x cube plus x4 up to infinite. Why we are able to write this function into this power series? Because first of all, this function 1 by x is differentiable, infinite times at x is equal to 0, first thing. And second thing is this series is convergent. Why? Because this geometric series with common ratio is x, and since mod x is less than 1, so this series is convergent only if mod x is equal to 1. If mod x is not equal to 1, then we can't write 1 minus, in fact then 1 plus x can't be written like 1 upon 1 minus x. This has to be written because the common ratio is less than 1. Then only the series is convergent. Okay. Otherwise this term will be infinite. So since mod x is less than 1, hence the series is convergent. Okay. Now same way, if suppose you have to there are three very key function we use here: e, cos x and sin x. These are three function we see. We'll see the expansion of these three things: e to the power x, cos x and sin x. Okay. So we will use this one, we discussed f0, f dash 0 x plus f double dash 0 x square upon 2 factorial plus f triple dash 0 x cube upon 3 up to infinite. Using this particular power series formula, we can find that e to the power x is 1 plus x upon 1 plus x is, this is 1, x square upon 2 factorial plus x cube upon 3 factorial plus x to the power 4 upon 4 factorial up to infinite. Same way we can substitute. In this case we can find the expansion of sin x is x minus x square, sorry, not x square, x cube upon 3 factorial plus x to the power 5 upon 5 factorial minus x to the power 7 upon 7 factorial and so on. And similarly we can write the cos x as 1 minus x to the power 4 upon, not 4 square, x square upon 2 factorial plus x to the power 4 upon 4 factorial minus x to the power 6 upon 6 factorial up to infinite. So these are the three key functions which is used in the derivation of the Euler form, and we have used this one. Okay, fx is equal to, so just like e to the power x, f0, since x substitute will get 1, and f dash 0, since x is e to the power x, differentiation is also e to the power x. Okay, so we know that if e to the power x is any differentiation, will always remain to be e to the power x. So f dash 0 is 1, f double dash 0 is also 1, f triple dash 0 is also 1. So that's why we are getting only the 1x, x square by 2, x cube by 3 factorial. Okay. So similarly sin x and cos x also. For example, f0, if I substitute cos x or sin x f0, so if substitute sin 0, this is 0, that's why it has no constant term, it start from here. Similarly cos x, if I substitute x equal 0, we'll get 1, so that's why it has a constant term. Okay, so we'll use these three expansion to derive the Euler form. Okay. For example, okay, we'll see all these things in a more detailed manner. We'll use these equations. So we'll use these equations to derive the Euler form. Okay, so let's write down in a separate manner, and one by one we will use this one. So let's say this is equation 1, this is equation 2, this is equation 3. Okay, we'll using the equation 1, using 1, e to the power x is equals to 1 plus x square upon 2 factorial plus x cube upon 3 factorial, so on. Substituting x is equals to I theta. I will get e to the power I theta is equal to 1 plus I theta square upon 2 factorial plus I theta cube upon 3 factorial and so on. Here we need to know that I square is minus 1, I cube is equal to I square I, that is minus I to the power 4 is 1, similarly I to the power 5 is I to the power 4I, that is I, and so on. It goes like this. Okay. So simplifying this, e to the power I theta is 1 plus I theta minus theta square upon 2 factorial and then I cube. So I cube is minus I, so minus I theta cube upon 3 factorial. Similarly, we get the plus theta to the power 4 upon 4 factorial and so on. Okay. Segregating the real and imaginary parts, so 1 minus theta square upon 2 factorial plus theta to the power 4 upon 4 factorial up to infinite plus I theta minus theta cube upon 3 factorial up to infinite. Okay, so basically we have the e to the power I theta, the real part is 1 minus theta square by 2 factorial plus theta to the power 4 by 4 factorial, whereas imaginary part is theta minus theta cube by 3 factorial plus theta to the power 5 by 5 factorial and so on up to infinity. If you look at this term 1 minus theta square by 2 factorial plus theta to the power 4 by 4 factorial, they are nothing but the cos term. We can see the cos theta will be 1 minus theta square by 2 factorial plus theta to the power by 4 factorial and so on. So the first term is nothing but the cos theta plus I, this term is the sin theta, this term is the sin theta. We can look at this, why it is sin theta. So theta minus theta cube by 3 factorial and so on is nothing but the sin theta is theta minus theta cube by 3 factorial plus theta to the power 5 by 5 factorial and so on. So basically e to the power I theta is cos theta plus I sin theta. Okay. Now if I replace theta with the minus theta, I will get e to the power minus I theta is cos of minus theta plus I sin of minus theta. So cos is the even function, so we will get cos theta, and sin is the odd function, so I will get minus sin theta. Okay. So we have the two things, e to the power I theta is cos theta plus I sin theta, and e to the power minus I theta is cos theta minus I sin theta. These are the two power, these are the conversion of Euler into a trigonometric form is a powerful tool or technique to solve the trigonometric identities, which we'll see in a while. Okay. So okay, so let's talk about some of the forms of complex number. Just a quick revision. So first form we already discussed is z is equal to a plus ib. This is nothing but the conventional or the standard form of the complex number, whereas z is equal to, let's say, mod z e to the power I theta. This is nothing but the Euler form of a, this is the Euler form of a complex number. Similarly, z is equal to a comma b. This is nothing but the ordered pair. This is the ordered pair form of a complex number. Similarly, let's say z is equal to mod z theta. This is nothing but the polar form of a complex number. This is the polar form of complex number. And this is also the mod z cos theta plus I sin theta. So this is also kind of polar form, but we call it a trigonometric form. So trigonometric form and polar form are same, almost same, because here also we need z and theta, here also we need z and theta. Okay. Okay, now one important thing. See, we have discussed how to solve analytically. So analytically, our Euler form is a very powerful tool to solve the problem. Whereas if you solve any geometrical problem, then it's a vector, 2D vector is a powerful method to solve the geometrical problem. Why? We had already discussed that in argand plane, we can treat the complex number as 2D vector. Complex as a 2D vector. Okay. Okay, so let's take some examples. Okay, so we have discussed that cos theta plus I sin theta is equal to e to the power I theta, and cos theta minus I sin theta e to the power minus I theta. Now let's take example. Let's take we have to find cos of 30 degree plus I sin of 30 degree square, cos of 60 degree plus I sin of 60 degree to the power q. We have to write in the standard form a plus ib. Okay. So quickly we know that this is cos theta plus 30 plus I sin 30 is nothing but e to the power I 30 degree. Okay. And this part is nothing but the e to the power okay, let's take more easier way. So we know that the cos 30 degree plus I sin 30 degree is nothing but e to the power I 30 degree, and cos of 60 degree plus I sin of 60 degree is nothing but e to the power I 60 degree. Okay. So essentially substituting these values here, we get e to the power I 30, I can write e to the power I pi by 6 and e to the power I pi by 3. So e to the power I pi by 6 square into e to the power I pi by 3 cube. Solving it, I will get e to the power multiply 2. So I pi by 3 into e to the power 3 cancel. So e to the power, so 3 by 3 cancel. So we will get e to the power I pi plus pi by 3. Okay. So now writing into the trigonometric form, we can have a cos of pi plus pi by 3 plus I sin of pi plus pi by 3. Okay. So it is minus cos pi by 3, because pi plus pi by 3 goes in the third quadrant, and third quadrant sin and cos both are negative, minus I sin pi by 3. Okay. And cos pi by 3 will be minus 1 by 2 minus sin pi by 3 is minus root 3 by 2 I. So essentially this trigonometric form is converted into a standard form using the Euler form. Okay, so Euler form is a powerful tool to solve any trigonometric form. Okay, let's take one more example based on that. Yes, let's take one more example. Let's say again 5 by 6 cos of 75 degree plus I sin 75 degree divided by cos of 30 degree plus I sin of 30 degree. So we have to write this complex number into the standard form, that is a plus ib. So again same manner we can say 5 by 6 e to the power I 75 degree and e to the power I 30 degree. This is nothing but 5 by 6 e to the power I 75 minus 30 degrees. So this is 5 by 6 e to the power I 30 minus nothing but 45 degree. So this is 5 by 6 cos of 45 degree plus I sin of 45 degree. This is 5 by 6 1 by root 2 plus I by root 2. So this is how we can convert this trigonometric form, a little bit complicated, into standard form using the Euler form. Okay. So let's take one more example. So by the way, one tool, that is JEE Main, we'll see in detail, but let's say this Euler form can also be used to easily crude form derive the JEE Main theorem. So JEE Main theorem. JEE Main theorem. What is JEE Main theorem? JEE Main theorem says that cos theta plus I sin theta to the power n is cos n theta plus I sin n theta. Okay. So now right now I'm not discussing what happens if n is integer or any rational or irrational. It's just a very simple form of JEE Main theorem I'm explaining. The detailed form we'll see in maybe in coming lectures. So this is anyway we know, if you want to see why it is happening, so this is nothing but e to the power I theta to the power n. This is e to the power I n theta, and is nothing but the JEE Main theorem. So JEE Main theorem is an indirect form of the Euler form. Okay. Let's take one example to solve this part. Okay. Let's say problem is, let's say if sin alpha plus sin beta plus sin gamma is 0, and let's say cos alpha plus cos beta plus cos gamma is 0, then we have to prove that cos of 3 alpha plus cos of 3 beta plus cos of 3 gamma is nothing but 3 cos of alpha plus beta plus gamma. Okay, we have to prove this one. See, for proving this one, see, I already discussed that the Euler form is a powerful tool to prove or to solve any trigonometric identity. These are some trigonometric identities. How can we prove? So we start since sin alpha and cos alpha is involved, we can start, let's say the any x is equal to e to the power I alpha, that is nothing but the cos alpha plus I sin alpha. And y is again e to the power I beta, this is nothing but cos beta plus I sin beta. And similarly z is e to the power I gamma is equal to cos gamma plus I sin gamma. Okay. Now if you look at this particular form, okay, cos 3, and then so it appears that it is something x cube plus y cube plus z cube, and this is something x into y into z. Okay, so by looking at this identity which you have to prove, we can think of the one algebraic identity, well known algebraic identity, that is x cube plus y cube plus z cube is equal to 3xyz, and this identity is valid if the x plus y plus z is equal to 0. Okay, now see whether this condition holds, or if this condition holds, then we can use this one. Now see what happens. X plus y plus z. X plus y plus z is cos alpha plus cos beta plus cos gamma, because x plus y plus z, so cos alpha plus I sin alpha, cos beta plus I sin beta, cos gamma plus I sin gamma. So we add this part plus imaginary part adding sin alpha plus sin beta plus sin gamma. Now observe that it is given that sin alpha plus sin beta plus sin gamma is 0, and cos alpha, cos beta, cos gamma is 0. So I can write this in nothing but the 0. Since x plus y plus z is 0, so we can say that x square cube plus y cube plus z cube is equal to 3xyz. So since x plus y plus 0, so therefore we can, applying the trigonometric, applying the algebraic identity, what is that identity? That is x cube plus y cube plus z cube is equal to 3xyz. Okay. Now what is 3x plus y plus z? I will substitute these values, so I will get e to the power I alpha cube. I will not, see, we can use this trigonometric also, but little bit difficult, so it's easy to write into the exponential form or the Euler form. Okay, this is beta is e to the power, y is e to the power I beta cube plus e to the power I gamma cube, and right hand side is 3 e to the power I alpha e to the power I beta e to the power I gamma. Okay, so this is nothing but e to the power I 3 alpha plus e to the power I 3 beta plus e to the power I 3 gamma, and right hand side is e to the power 3 I alpha plus beta plus gamma. Now writing into the trigonometric form, we'll get this is nothing but cos of 3 alpha plus I sine of 3 alpha plus cos of 3 beta plus I sine of 3 beta plus cos of 3 gamma plus I sine 3 gamma. This is nothing but the 3 times e to the power I alpha, that means cos alpha plus beta plus gamma plus I sine alpha plus beta plus gamma. Okay, now comparing the real and imaginary part. What is the real part? Real part on the left hand side is cos 3 alpha plus cos 3 beta plus cos 3 gamma, and right hand side it is nothing but the 3 times cos of alpha plus beta plus gamma. So this proves our given identities, but we can also same way we can prove the sine form also. So comparing the imaginary part, we will get the same way. The imaginary part means the sine alpha 3 alpha sine 3 beta sine 3 gamma. The right hand side, the imaginary part is this 3 into I sine alpha plus beta plus gamma. So comparing the imaginary part, we will get sine 3 alpha plus sine 3 beta plus sine 3 gamma is equal to 3 sine alpha plus beta plus gamma. Okay, so this is how we can prove the real part and imaginary part.